Okay, so I think it's time. Our next speaker is Professor Mercurio from UCLA, and he will talk about cohomological invariance of algebraic groups.
So the notion of cohomological invariant was introduced by Seb about 20-25 years ago, and I'm going to discuss this topic. But before, I would like to start with some ingredients of the proof, or of the definition of an invariant. So the first ingredient is the notion of a torsor, G torsor. Well, G is an algebraic group over a field. Well, I would like to write F. Well, if I start writing K, I will switch to F anyway. So I don't assume that G is smooth and F is algebraically closed. So arbitrary F, arbitrary G, will make a finite type over F. Well, we have a very nice action of G on itself. Looks like G acting on itself by left translations. And this is a regular action. Stabilizer is trivial and action is transitive. We can try to generalize this to a more general variety. So we assume that G acts on variety X. Still regularly. Okay. You can think of it as when you extend scalars to, say, algebraic closure, X becomes isomorphic to G with the regular action of G on itself. So it's a nice regular action. And we say that G is a G torsor over the point. Well, if X has a point over F, then the map from G to X, taking G to Gx, where X is a fixed point over F, is an isomorphism of G torsors. So in other words, every G torsor with rational point is the same isomorphic to the G, which is called the trivial G torsor. So a torsor without point, of course, cannot be trivial because it cannot be isomorphic to G. G has a point over F. So the torsor is trivial if and only if it has a point over the ground field. So if the ground field is algebraically closed, then of course every torsor is trivial. Or if someone thinks that varieties must have rational points, then for these people, all torsors are trivial. And well, Sir visited UCLA some time ago, and he told us the following story. So once a group of physicists approached him and asked, "What are you doing, sir, in algebra?" And he says, "Well, I'm doing torsors over a point, principal homogeneous spaces over a point." And then he said the physicists didn't get very excited. So X should not have any point when you want something non-trivial. And here is an example. Let's look at the unit circle. So it's a group. Small group with characteristic is not true. Multiplication mimics the complex multiplication. And let's pick any element A in the field and consider variety XA given by the following equation. X squared plus y squared is equal to A. So clearly there is an action of G on XA just by complex multiplication essentially, making XA a torsor, because every two elements with this property differ by unique unit in the circle. So this is G torsor. Well, when it's trivial, when this equation x squared plus y squared equals 8 has a solution in the ground field. And it may have no solution if ground field is field of real numbers and a is negative. This guy has no points over the reals, and it is example of a non-trivial torsor for G. Well, you can consider families of torsors of this type. They also called torsors. Consider the following situation. G is a group, and you have a morphism of two varieties, x to y. G acts on x, and G acts on y trivially. And you want to have the following, that any fiber of this morphism, fiber of a over any point of y, of course it has this action of G on it. And we would like to make this fiber a torsor over the point of definition, point you choose first in y. So it can be viewed as a family of torsors over y. Well, there are several ways to define torsor. You can make base change from y to x. So here you get x times x over y. And you would like this to be a trivial G torsor. A trivial G torsor is G times the y.
Times x?
Times x. Yeah, oh, x, of course, yeah. X. So the natural morphism which arises should be isomorphism. So in other words, the base change of this gadget is a trivial torsor. And there's also a geometric condition, this map should be faithfully flat. Again, well, this notion is very, such a thing is called the G torsor over base y. It's a very nice relative notion. It allows pullback of any torsor is a torsor. In particular, if you have a G torsor and a point of y over some field, say k, which is a morphism from spectrum of k to y. For k, you can take any field extension of f. So the base change is going to be a torsor also, but over spectrum of k. So G torsor over point. Well, I would like to make another example close to the first one. Let's take for x a2 minus the closed set of points xy such that x squared plus y squared is 0. Okay, take the open set where x squared plus y squared is not 0, and map it to Gm, the multiplicative group, by taking xy to x squared plus y squared. Well, there's an action of that G of the unit circle on x, which makes this G torsor. If you take any point of Gm over some field, in other words, you take any element of the multiplicative group of some field, you view this element as a morphism from spec k to Gm. The pullback is indeed just exactly that G torsor of the point, xk. So we have a family of XAs where A runs over all non-zero elements in the field. So those torsors are classified by points of Gm. In fact, this torsor has an extra property that every torsor over a point can be obtained by the pullback. It turns out very easy to check that such XAs are all possible torsors over the spectrum of K. So every torsor over a point arises from that one by a point in the base. And such torsors are called versal torsors. So E over Y, which is a G torsor, is versal. Well, if for every torsor I over spec K, for K field extension of F, arbitrary field extension, there is point Y over Y of K, and a fiber product diagram. Pullback diagram, E goes to Y. Here's the spectrum of K going to Y by the point Y, and this is the torsor I. Well, by technical reason, actually, K is assumed to be infinite, which is a restriction, of course, only in the case when F is finite. So for any infinite field extension, you have such a property. How do you build versal torsors? There are two ways to make those torsors for a given G. The first possibility is that you embed G into GLN. Oh, I didn't say that G is linear, it's linear algebra at the very beginning. GLN.
Why do you avoid the case where K is finite?
Well, at some point you will need
For
an
rational.
open set and define variety having a point. Probably not really very strong restriction. Okay, G is in GLN, and then we take the following torsor GLN to GLN mod G. It's versal. It's G torsor and versal. Another construction is as follows. You take a representation of G which is generically free. G representation. In other words, the stabilizer of a generic vector is the trivial group. So acts almost freely on V. Then it turns out that you can always find an open G equivalent subset, non-empty. So G acts on U, such that there exists a G torsor from U to some other variety which we call U mod G. And this is also versal. So over a finite field, this may have no points. Well, now I would like to give examples of torsors over fields. Examples of torsors. First example, G is finite. So what is a torsor for a finite group over a field? Every torsor has the following form. It is a spectrum of some L. I will tell in a second what L is. The spectrum of F, if we do torsors over the base field F, G must act in here, so L is an action of G, and L is algebra over F, and in fact it is what is called G-Galois algebra. So L is a G-Galois algebra. If it is a field, you just have the Galois extension of L over F with the Galois group G.
Is G smooth or
No.
no?
What?
Is G étal or
Sorry?
is G smooth?
G? Finite. Yeah, when I say, yeah, finite means discrete group.
Okay.
Yeah, finite discrete group. The second type of examples, well, I'm going to be a little bit imprecise. So let's take an algebraic object, A. Well, by that I mean some structure based on a vector space with certain properties, like an algebra, for example, or algebra with involution, algebra with some properties like central or simple, or maybe a quadratic form based on a vector space, things like that. So we also have the base change structure. You can consider this object over field extensions of base field F. Then we also assume that G, the automorphism group of this object, has the structure of an algebraic group over F. Okay, then we define twisted forms of B, of A. B, also another algebraic object, is a twisted form of A. If when you go to some large field extension, B becomes isomorphic to A. If B, say, over separable closure of the base field is isomorphic to A over the separable closure. So if B is a twisted form, then you can look at morphisms between B and A, and you assume that there is a structure of algebraic variety on this, that is X. So if B is not isomorphic to A, then it has no points over the ground field, but it does have points over separable closure because of this condition. And there is a natural action of G on such an X, and the action is very nice. It is regular. And in fact, well, in most of the cases, X is a G-torsor. So we get a map between the set of isomorphism classes of twisted forms of A to the set of isomorphism classes of G-torsors. Let me write like this: torsors for G over F. And in many interesting cases, this map is a bijection. The map, of course, takes a twisted form B to that variety X of, well, not morphisms, isomorphisms. Isomorphisms between B and A. And this very nice property, it relates really algebraic objects. I will give you examples with the torsors. So examples of this situation. Let's take PGLN, and PGLN is the automorphism group of the algebra of matrices, Mn over F. Now, what is the twisted form of the algebra of matrices? Twisted form of Mn is a central simple algebra of degree n, essentially by definition. So we get bijection between central simple algebras of degree n, of dimension n squared, over any field and PGLN torsors. Over F. Second, let's take symmetry group. Symmetry group is the automorphism group of another algebra, namely the product of n copies of F. The only thing you can do with Fn is just permute the components. What are the twisted forms of Fn? Those are étale algebras of degree n. So étale algebras of degree n over F are in one-to-one correspondence with Sn torsors, which is, by the way, the same as a Galois algebra with the Galois group Sn. So there is one-to-one correspondence between étale algebras of degree n and Galois algebras of degree n factorial with the Galois group Sn. Well, I take a non-degenerate quadratic form. Over F. And the orthogonal group of Q is, of course, the automorphism group of this object, of Q. And the twisted form of non-degenerate quadratic form, well, at least in characteristic not 2, is also a non-degenerate quadratic form. And every two forms over separable closure are isomorphic. So you get all quadratic forms of the same degree n, dimension n. Over F. And one-to-one correspondence with O of Q torsors. Well, many algebraic groups are automorphism groups of some nice objects. Well, maybe last example. G is the group of type G2. And the split one is isomorphic to the automorphism group of the Actonian algebra, or Carey algebra. Actonian algebra. Non-associative dimension 8 algebra. And the twisted forms of Actonian algebra is called Carey-Dickson algebra. So we have one-to-one correspondence between isomorphism classes of Carey-Dickson algebras. And G2 torsors. Okay.
Do you have examples where, interesting examples where it's not bijective?
Not biject?
Yeah, not one-one correspondence.
Well, actually, I didn't look for such examples. I tried to find just the opposite, and it's isomorphic. So this precise statement, I don't want to actually make precise statement, but as I said, if the algebra, well, the object A is attached to some vector space, so for example, is given by one or several tensors on this vector space, or more precisely, there is a representation of a group in GL of the vector space, then we always have bijection. By the way, this object may be even of infinite dimensional nature. It itself could be a group. So you can take a group, algebraic group, and then the automorphism group of that group is another algebraic group, and you can apply this statement. And algebraic group is also attached to a vector space, namely the vector space of regular functions on the algebraic group. And so you do have bijection in that case as well. Well, the other ingredient of the definition I'm going to discuss is the following topic, Galois homology. So we have field F, and take a separable closure of F, it's a Galois extension, and write gamma for the Galois group of that extension. And let M be an abelian group with the action of gamma, so it's gamma, continuous gamma module. We simply say Galois module. So we can define the Galois homology group of gamma with coefficients in M, and we'll simply write Hn F M. Well, H0 is, of course, the group of invariant elements, M gamma inside M. There are a few nice Galois modules. For example, you can take G M, the multiplicative group. Well, more precisely, maybe I will write the invertible elements in the separable closure of F. You can take the group of roots of unity, mu n. Well, that makes sense if n is relatively prime with characteristic of the field. So P, characteristic of the field, if positive, does not divide n. Or you can take any finite group, or infinite group with trivial action, Z mod n Z, and so on. And here are important calculations. First of all, H1 F separable closure is 0. This is Hilbert-90 theorem. H2 F set star is the Brouwer group of F. The group of equivalence classes of central simple algebras over F. H1 F mu and F star modulo F star square to the n. H2 F mu n, the n part of the Brouwer group, elements of exponent n in the Brouwer group. Well, ramification. Suppose we have a field extension of F and a discrete valuation. k over f, trivial of on f. Well, the valuation gives you a homomorphism from k star to z. Well, evaluation is a homomorphism. When you factor modulo n, you get this map. The first is the group H1 k mu n, and the second is H0, actually of every field, but let me write the residue field k of v here, z mod nz. And this is the residue map, which lowers the dimension by 1 and makes something with the module. So the general construction is as follows. Suppose you have a Galois module n, such that n kills the n, for some n. Then you can define the twists of m. Well, I will m of minus 1. M of minus 1 by definition is home from mu n to m. So the residue map is the map from any degree, say d, of field k with coefficients in m to hd minus 1, the residue field, k of v, and then m twisted by minus 1. It's a residue map. And we say that an element u here is unramified with respect to the valuation if the image of the residue map is 0. Well, this works only if n is prime to characteristic, to the characteristic of the field. Okay. Well, now I can finally give definition of an invariant.
In that definition, you're assuming that M is itself an unramified Galois module?
What is unramified?
Are you assuming that capital M is itself an unramified Galois module? So the right
No,
side.
n is just any Galois module. There's no notion of ramification.
So how did, for the right side, you want the
Oh,
Galois
yeah,
group of
yes.
the residue field?
No, it doesn't matter. It's Galois module over f. That's what probably you mean. For yes, it's over f.
Over
That makes
F.
sense.
Sorry, okay.
So G is an algebraic group. And M, the Galois module over F. And also D is a non-negative integer. And I consider the two categories. The first one is the category of field extensions of F. The objects are field extensions, finite or infinite. All homomorphisms are homomorphisms of fields over F. And that category is the category of sets. And we have two functors from first category to the second. The one takes a field K to the set of isomorphism classes of G torsors over K. And that functor takes the same K to actually the group H D of degree D of K with values in M. Okay, and an invariant of G of degree D with values in M isomorphism between these two functors. So it's map of sets for any k from the set of torsors to the set of homology elements, and it should be natural in K. So we have natural commutative diagram for a field extension. So what happens is that you assign to every torsor an element in the Galois homology. You want to study torsors by means of Galois homology. Well, let's call it I. If you have two invariants, you can add them because this is a group. So you have an abelian group of all invariants of the same group G with values in M and invariants of given degree D. So it's a group of all such invariants. Yeah, and we would like to study this group. Well, the best you can do is just compute this group. So why is this interesting? What may happen is that you can classify torsors by means of the invariants. If the two torsors are isomorphic, of course, they have the same invariants. Sometimes the converse is true. If two torsors have the same invariants, they are isomorphic. It happens for some groups, for some not. That's one possible application. The other application is to detect rationality of certain varieties, and I will discuss this later. Now I would like to make first remarks about this group. First of all, you have always build a constant invariant, which takes every torsor over K going to the fixed element UK, where U is the Galois homology class of the base field. So you fix U, and then it is very stupid invariant sending everything over K to, not to U, but to U lifted to K. This is called a constant invariant. So this group contains a group of constant invariants, which is not really very interesting. And every constant invariant is given by HDMF, so it's isomorphic to HDMF. FM, sorry. Well, the other thing is that those two sets, in fact, have a distinguished point. So we do have two functors to the category of pointed sets. The torsors have the trivial torsor inside the distinguished point, and here we have 0. So an invariant is called normalized if it takes trivial torsors to 0 always. So you have the subgroup of normalized invariants. And of course, every invariant can be modified uniquely by a constant invariant to get normalized invariant. So essentially, it is sufficient to study the group of normalized invariants. Well, I would like to give a few examples of invariants. In fact, in nature, we already have many invariants. We didn't know that those are of this form. Well, the tautological invariant of a central simple algebra. we take the PJLM. The group whose torsors are central simple algebras of degree n. And if you have a central simple algebra of degree n, a central simple algebra of degree n over any field K, it has the class in the Brouwer group of K, in fact, of exponent dividing n.
A.
A. Class of A.
And this is H2 F mu n, K mu n. So it's a degree 2 invariant, which we call the tautological invariant. It's variant of degree 2 of PJLM with coefficients in mu n. It contains a tautological invariant. And we know that two algebras of degree n are isomorphic if and only if they have the same class in the Brouwer group. So just that one invariant determines the torsor up to isomorphism. And for the purpose of classification, you don't need other invariants. But for the other problem, you certainly would like to have more invariants of this group. And it's a very wide open question to determine the group of invariants of degree D with values in mu n or z mod n z. We know very few of those. Second, you can take quadratic forms. Well, let's take the split group ON, well, S or ON, the orthogonal group. Well, the torsors for the orthogonal group are quadratic forms of degree n. You take a quadratic form Q of degree n. In characteristic node 2, you can diagonalize it. It is just the sum of AI xi squared. AI are the coefficients. You can view AI inside the multiplicative group modulo squares. Well, it's a quadratic form over K, so the coefficients belong to K. And that is H1 F mu 2. Characteristic is not 2, the same as H1 F z mod n z, z mod 2z. Well, if you vary dimension, you will get a graded ring. You can take the cup product as the product in that ring.
Maybe that should be K.
Hmm?
The F maybe should be K.
K, yes. And you can define the following things. You can take the product of some number of those elements. Say, take S, at least one. And you take the cut product of S elements, I1, I2, AIS, and take the sum over all permutations. Well, sorry, you have to take the sum of over all tuples I1 less than I2 less than IS. And this is going to be an element in H2, HS of K Z mod 2Z. And it turns out that this is independent on the choice of diagonalization. And it is called the Stiefel-Whitney invariant of degree S, the WS of the form Q. Whitney invariant. They are non-zero for I from 1 to S. So the group of invariants of the orthogonal group with values in Z mod 2Z contains those or Stiefel-Whitney invariants, and these are all the invariants. Linear combinations of those form all possible invariants of the orthogonal group as well as in Z mod 2Z. What is W1? W1 is the determinant, or discriminant of Q, living in K star modulo squares, which is H1, K Z mod 2Z. What is W2? W2 lives in H2, K Z mod 2Z. It is the two part of the Brown group. And it is almost the Clifford invariant of Q, class of the Clifford algebra. Well, wrong Clifford. Okay, how to compute that group of invariants?
Is there interaction between the invariance degree and the n, for which where n is
Oh, yes.
roots of unity?
N, up to N, of course. Yes. Yes, the invariant of degree N, the largest one. How to compute this group? You take a versal torsor for the group G. Say E over Y, E over Y, and the versal G torsor. And look at the generic fiber of this versal G torsor. So the spectrum of the generic point, spectrum of f of y, the generic point of y, and the fiber product is called the generic torsor. If you go back for a second to our example with the circle, the generic fiber would be given by the equation x squared plus y squared equals t. T is a parameter. And when you specialize t to any value, you will get all possible torsors. That's the idea of the generic torsor. You specialize to any other torsor. If you have an invariant I in a group of invariants of degree d of G with values in M, you can evaluate this I on every torsor. In particular, you can evaluate I on the generic torsor. You will get the generic value in HD and the function field of Y with coefficients in N. In other words, you get a map phi from the group of all invariants so that H D f of y f, taking an invariant I to the value at the generic invariant, at the generic torsor. Well, there are three theorems about this map. The first theorem of Frost saying that phi is injective. In other words, every invariant is determined by the value at the generic torsor, which is not surprising because generic torsors have information, contain information about all possible torsors. But the proof is highly non-trivial. Okay, the second theorem and third theorem tells us something about the image of this map. The map is, of course, not subjective. The target group is very big. It turns out that the image of phi lives in a smaller group. Let me introduce notation. Let's take Y variety. We will apply it for the variety from the versal torso Y. And we assume that it's smooth. I should have said that, well, now we assume that Y is smooth. It is certainly smooth in all the constructions I will well, take any point of codimension 1, any reducible device. Then the local ring is at Y is regular of dimension 1, so it's discrete valuation ring, DVR. So we have a discrete valuation associated to a point of codimension 1, Y, of the function field. Discrete valuation on f of Y. So we got the residue map, let me call it to Y from HD, the field f of Y, M, to HD minus 1, the residue field M minus 1. So I will write A0 Y HDM for the intersection of kernels of all these maps. So this is a subgroup in D f of ym of all elements unramified with respect to points of codimension 1. It is much smaller group than the whole group. And the second theorem is due to Serre, that the image of phi is inside that group. So in other words, the image of phi is unramified with respect to all valuations coming from points of codimension 1. And then, in certain cases, it is equal to that group. Well, maybe I should have said at the very beginning that the assumption is that M is torsion, and this torsion is relatively prime to the characteristic of the field. Although many things can be extended to the case when M is arbitrary and include the P part here as well. So let's say just torsion module. So the last theorem of Tataram that if the versal torsor is obtained by the second procedure I mentioned, U mod G, where U is open and G equivalent in some generically free representation, and assume that the codimension of the bed points V minus U in V is large enough, namely at least 2, then phi is, the image of phi is just that good.
Does G have to be some nice thing? G is any algebraic group? Or like
G
semi-simple?
is any algebraic. But it probably reduces to the computation of that group. And, well, I would like to prove something today. I would like to, I told this proof is complicated, but I will try to explain it in 5 minutes. So the phi is injective. Y is invariant determined by the value at the generic point. Let's take any invariant I. And assume that it has trivial value at the generic point. And you need to see that I is 0. So it's 0 at every other torsor over any field extension. So we need to start with a torsor over some field extension. Let's take E, a G torsor over K. K is a field extension of F. And what we need to show is that the value of the invariant of E is 0. Well, by changing the base field from F to K, we may assume that K is equal to F. Let's do this. Now we have the following objects. We have the variety Y. We also have the torsor E, the versor torsor. We have the spectrum of K, and maybe I should have used some other letter, E prime. E prime, the torsor over spectrum of F. And since E over Y is reversal, you can take E prime as a pullback with respect to some point Y. Y is a point of Y over the rational point of Y. Well, we also have a local ring at this point. Call it O, and you can take the completion of this ring. The Y is on a singular point, so it is the ring of power series in some number of variables. And that L tilde, L is the function field of Y, and L tilde is the completion of this field with respect to the valuation, with respect to, well, L is the quotient field of O, and L tilde is the quotient, L hat is the quotient field of O. It's the completion of the field f of Y with respect to that local ring. Okay, so here is Y. Then we have the spectrum of the completion. We have the spectrum of the base field F, and we have the spectrum of L hat. Well, there is the two canonical maps to Y, and then this is the point Y. There is a map from spec F to O hat, of course, given by reduction to the maximal ideal. And that square is commutative. We have not square, a triangle is commutative. We have another triangle that is with respect to the embedding. And this is also given by the embedding of F into a larger field. And this map is the embedding of F into the completion. And here is another commutative square, triangle. Okay. We start with a torsor over a spectrum of F. That was E prime. E prime. And we make E prime as a pullback of the versal torsor E over Y with respect to the point. So E prime is a pullback of E. On the other hand, you can pull back E to the spectrum of the completion. So that's right, E, O complete. And then when you do the pullback with respect to this vertical arrow, you get E prime. And now comes the Hensel's lemma. So the completion is nice local ring. This one is residue field K. And Hensel's lemma for torsors says that the torsors of over F and over this completion are in one-to-one correspondence. And those correspondences can be given either by the pullback with respect to this down arrow or the other arrow. So the maps, the pullbacks are exactly those inverse to each other by ejections. So E prime comes from E O hat, and conversely E O hat comes from E prime with respect to the other arrow. Okay, now look at the second triangle. You pull back E O hat to L hat, and what is this? This is the following. You could have come first from E to the function field of Y, which is a generic torsor, and then extend to the larger field. So it is the same as the E generic to L hat. And it's the same as if you pull back E prime with respect to this arrow. Okay, finally, you see that all these four torsors correspond to each other with respect to those pullback maps. And we now look at this arrow corresponding to the extension L hat, very large field, over F. And you write the corresponding homomorphism on the homology group, HD FM to HD L hat M, and must take by functoriality the value of the invariant E prime over, invariant was called I of E prime. It goes to I of E generic, and then lifted to L hat. But we assume that the value at the generic point is 0. So this is 0. And finally, the ring O, well, I never expected to switch from F to K. In my life, only from K to F. Okay. So the local ring is the ring of power series. This stuff is also the ring of formal power series, field of power series. And for such an extension, you can see that the map on homology is injective. And therefore, this is 0. And that is the end of the proof. So Ross told me that he explained this proof to Sarah during some phone conversation, and it was the most expensive phone call in his life. So the proof is not very short. Okay. So.
Are there any questions?
In your last term on Totaro, you had an obstruction codimension 1. Why?
Mm-hmm. Yes. Well, you see, you have the variety U open set in the vector space V, and you can make it smaller and smaller by deleting divisor by divisor. And when you make it smaller and smaller, you change the group of unramified elements because you delete those divisors. So you have the group of unramified elements. If U prime is smaller than U and the difference is a divisor, the group of A0, U mod G, HD is smaller than this group because you deleted evaluation. Okay, this is not equal. So theorem cannot be right for for this group because the image is contained in a smaller group. You cannot delete the divisor when you do the change of the open set. But if you only delete the points of codimension 2 and higher, you still have the same divisors given by the variety. Okay? The variety, the set of points of codimension 1 is the same if you delete divisors, if you delete closed set of codimension at least 2. That's it.
Are there any other questions? If not, let's thank Professor McLeod. Our next talk is in 25 minutes in the room that we had the first lecture today.
In the other building.
The other building, yes.
But the same, different room, same room?
I think it's the same.